Okay, good morning, everyone. It's my pleasure to introduce Professor David Bader. He is a professor and a founding director of the data science department of the data science program at the New Jersey Institute of Technology. Before that, he was a founder and chair of the computational science program at Georgia Tech Institute. He has won several awards and distinctions. I'm going to say only a few of them. He's a fellow of the IEEE, ACM, AAS, as well as SIAM. And he advises the White House on the National Computing Initiative strategies. And he has several projects and has led many distinguished programs under his leadership. Today, he will talk about a little bit about data analytics and grand challenges in performance data analytics. Over to you.
Thank you, Govind. And again, I'm very grateful for Govind hosting my visit today. It's been probably about 20 years since I last visited the Indian Institute of Science, and it's just a beautiful place. I'm glad to be back here. Being able to talk to you about something I'm very passionate about, which is really solving global grand challenges using high-performance data analytics. And that involves high-performance computing, data science, and parallel processing. And I'll tell you a little bit more about it, but we're very applications driven. We look for real world problems and we architect solutions to them. So Govind already introduced me, and I also received an award last year, the IIIE Sidney Firmback Award, that I'm really proud of, because as a brand new faculty member some decades ago, many years ago, I created the first commodity-based supercomputer using Linux, the Linux operating system. So recently, 2019, I moved to the New Jersey Institute of Technology and launched a new Institute for Data Science and a Department of Data Science this last fall with bachelor's, master's, and PhD programs. It's a very nice school. It's located very close to New York City, where I live. And I have about 40 faculty involved with my Institute for Data Science. And we're really focused on real world problems, solving problems that affect humanity, society, and people, as well as our planet. We have a number of centers, a center for big data, a center for cybersecurity research, one involved with medical informatics, a fintech group because we're in the heart of the fintech sector, and also a new center on machine learning and AI. So it's a very vibrant, research-oriented university, and we do a lot of real-world partnerships with industry, and with other laboratories as well. My group also gets funded and supported by a few companies. For instance, we have an NVIDIA AI Lab Award, or NVAL, where we're building graph analytics into open source packages like Rapids AI from NVIDIA to accelerate data science with NVIDIA GPUs. We also have received support from Facebook and their AI systems group, where we're looking at graph learning algorithms like representation learning, and to look at scaling these problems beyond academic sizes to really what the enterprise needs. But today's talk, I want to talk about data and the work that we're doing with large-scale data analytics. I think about data in terms of these two axes, where the x-axis I have represents objects that we're looking at, from known objects on the left to unknown objects on the right. And then on the y-axis, I have patterns, from known patterns on the bottom to unknown patterns on the top. And I like this quad chart because it lets me talk about the types of problems that we have in data science. For instance, in the lower left, where we have known objects and known patterns, is where relational databases have done quite well since the 1980s, where we can have schema that describe objects. For instance, you are a customer at a store, you have a record about yourself, your name, your address, your phone number, your email address. You have every product has a record in the store, a SKU number, which is a product ID. And then when you check out, you have a shopping cart that ties the customer with the different items that you purchased. And so since the 1980s, for 40 years, we've known how to solve analytic problems and questions quite well in this space. On the off diagonals, these quads, for instance, the upper left, where we have known objects but unknown patterns, an example of this type of problem occurs in cybersecurity, where you may have a CISO, a company chief information security officer, that is looking within their organization, and some individual trips some security tripwire, and you want to understand, what are they up to? Are they in collusion with other individuals? Are they trying to exfiltrate IP and very important information, source code from the company? Or was it just accidental that they went to touch this file that they didn't have access to? So this is where you have known objects and you want to explore around to see if there's some pattern that's occurring. And also in the lower right-hand corner, this is sort of an inset subgraph isomorphism problem or template matching, where we have a graph template, that's what's inset here, and we want to search around that, looking for that pattern in some known or observed data to see whether or not that pattern exists. So in the 1990s, we had vertical databases that have been very good at solving problems of these two domains. But often we get problems where it's more discovery in this top right quadrant that I call unknown unknowns, where we don't know what objects we have and we don't know what patterns we're looking for. If we haven't seen the data before, then it's very hard to train machine learning, because machine learning works very well when we have known patterns. But when you have unknown patterns or novel patterns, this becomes a very hard quadrant to search. And this quadrant is where we often have our biggest surprises. For instance, the novel coronavirus, COVID-19 that spread, which we hadn't seen on this planet before. Or when there's a novel zero-day cyber attack that we haven't seen before. So anytime there's something that happens new that we haven't seen before, we're trying to search this data for things that we don't know. And so what I try to do is help analysts to understand what's in that fourth quadrant of unknown unknowns. Sure, question.
Social network problem, we put it in on fiction.
So social network problems can occur in several of the quadrants here. So for instance, on the upper left, where I've known objects, for instance, in a social network, I may know who all the friends are, but there may be some, for instance, malicious actors, or there may be misinformation being spread within that network, and I don't quite know what the pattern is, so that's an example on the upper left. There's also cases where I may collect information and not know anything about the social network or what questions to ask about the social network, and that would be in the upper right. And I'll give some examples in this talk on where that fits in. Great question. And through this talk, I'll talk in terms of social network analysis because we understand a friendship network. For instance, Govind and I have an edge connecting us on a social network because we're friends with each other. However, that abstraction is very powerful, where we have many systems where the vertices represent objects, people, places, things, and the edges represent relationships between them. And so many of these problems, from healthcare, massive social network analysis, business intelligence, systems biology, resilience in the electric power grid, even the full-scale modeling and simulation of entire nations, looking at their social, political, and economic models, requires this understanding of how these objects interact with each other. So we work on problems in many of these spaces, but we often talk about it in terms of a social network algorithm and who is at the core of a social network, who is moving between different communities and doing community detection, etc. So we like to talk about things in a social network, but understand that the abstraction is very powerful to be able to analyze graph data science in all of these places. So for instance, in social networks themselves, oftentimes we get very large data sets where we're trying to understand communities, and that may be existing communities and how they change around, or potentially there are new communities that form over time, or other communities that dissipate, and we want to be able to detect that. Also, communities may not just be a partition of the vertices, communities may overlap with each other. For instance, I'm in one committee because I'm a professor at the New Jersey Institute of Technology. I'm in another committee because I live in Manhattan in New York City. I'm in another community because I love to travel to India. And so these are overlapping communities. We're not just in one community, we're often in many communities. And so we want to understand how to tease apart those different communities within these types of networks. So when I talk about graphs, there's many types of graphs as well. I have just pulled out 3 examples here to give you a flavor, where the left-hand graph comes from astrophysics, the middle graph comes from bioinformatics, and the right-hand graph comes from social informatics or social networks. In these cases, often there's different algorithms that we want to exploit on the data sets. There's different challenges to the type of data that we've collected, and there's different scales to the problem. And these data sizes, the heterogeneity of the data, and the quality of the data are really new challenges that we face as we're trying to do graph analytics on these various types of graphs. So for instance, in astrophysics, there are very large data sets that are sky surveys, and often we may be looking for events like trying to find an outlier that could be a quasar where we want to turn a radio telescope to look at that quasar. So we look at multiple images, and if there's an outlier, we want to figure out, is that outlier just some noise in the images or some piece of dust, or is there some event that we want to see? And so the challenges in these cases are often that there are temporal variations and really big data sets that we need to process, some of the largest scientific data sets, in fact. And then the graph problems that we're looking at are either going to be like clustering or matching type of algorithms. For bioinformatics, we have challenges in that the data may be very heterogeneous and the quality may be different depending on which lab sequenced information that we're using. And we may be trying to identify drug targets and protein interaction networks. So the graph problems that we're looking at may be algorithms like centrality or clustering to find the central proteins within that network. Or on the third case, the social network problem itself, we may have new analytic routines that we want to run as we're trying to figure out new properties of how the communities change over time. There's a lot of uncertainty in the data. For instance, all of us in the room may be friends, but we may not have links together in the social network. So we have missing edges, or there may be someone that friends me that I don't know, but I accept anyway. So in real life, we're not really friends, but yet we're connected to each other. And so there's data uncertainty, and we may be trying to discover emergent communities or model the spread of information in these networks. And the types of algorithms that we're trying to compute often are algorithms like flow algorithms, clustering, shortest paths, and the like. So even though we have graphs, there's so many types of graphs. It's really interesting because we get to design new algorithms. And also, if we know something about the graphs and the data sets, we can tailor new algorithms that run very well on these.
We take different types of graphs. I'm a little bit worried from a graph theory point of view. How these directed graphs, weighted graphs.
Correct.
That's all that I have. Like,
so
what else do we see in terms of types of graphs?
I have the slide hidden where I actually answer that question, but I cut it for the sake of time. So many graphs that we have could be simple graphs, or they could be multi-graphs where you can have multiple edges between vertices. Some are directed, meaning that edges start from one vertex and are oriented towards a second vertex, or they could be undirected. I could have weights on the vertices or unweighted. I could have weights on the edges or unweighted. I could have timestamps. I could have a property graph where every edge has a vector of properties associated with it. I can have hypergraphs where really I have units that are collections of vertices, and even more. So those different types of graphs often lend themselves to different types of algorithms, or we can customize the algorithm if we know, for instance, it's a weighted graph or an unweighted graph.
We're also looking at time varying graphs, like graphs in which it is kind of clear.
Yes. So much of this talk, I assume that the graphs are coming from streaming data sources. And when I first started doing graphs, I thought every graph was static. That's the way life was. You have a data set, you put it into the computer, you run your graph algorithm, you get your answer, and you're done. When I was an undergraduate taking a graph theory class, that's the way life was. I had an algorithm, and there's always one input and one output. In reality today, all data is streaming. Whether the streams are coming to us through an infinite fire hose every millisecond. For instance, we're doing network traffic analysis for cybersecurity, and in milliseconds, we have to make decisions based on the packets that we're seeing. Or maybe running a problem where
I think you want the question to be repeated, but next time onwards you can pass.
Oh, sorry.
Yeah, that's okay. I'll take it.
So lost my train of thought. So the question was about are there different types of graphs, but I forgot where I was at.
I think you continue.
Okay. So one area that we've worked is resilient power grids, and this turns out to be a graph problem as well. So over here is just a view, and in the US, we really have just 2 or 3 power grids because they're interconnected. The east part of the US, the west part of the US, and the state of Texas down in the bottom is kind of a separate grid. And we use graph analytics to analyze these. It's very important if your power grid goes down, people depend on it for food, water, transportation, heat or cooling, and so it affects people's lives. And this is a very important problem. Also in the space of intelligence and surveillance, we see a lot of graphs. For instance, on the top is a graph that represents the September 11th terrorists that attacked the United States back in 2001. And it was argued that if we could have run an analytic called between centrality, we would have been able to pick out the hijackers on the plane and even the ringleader for the entire operation. Or down on the bottom, this is also a graphic. Again, I have sources given for these public graphics. Down on the bottom comes from communications of the ACM, but it's the subgraph isomorphism problem that I mentioned previously, where you have 2 people, they are living together in a house, one rents a truck, one buys fertilizer, and they're observing some place of work, some business. And so that is, no, thank you. So that is an example of a graph template that we may be looking for some version of it, something close to it in the real graph. And so this is either exact or approximate graph matching. And also some other example cases in healthcare. This is some work that my former student, Kamesh Maduri, now a professor at Penn State, and I did. And this is just the answer slide of a whole talk where we used the between centrality algorithm in graph and network science and applied it to the human proteome, at the time 44,000 proteins when we did the study. And we were also the first group that parallelized the between centrality algorithm, and we applied it to this data set. What I have here is the degree on a log scale of the number of interactions every protein has in the human proteome that we knew about back in 2006 when we did this work. And on the y-axis is a log scale of the normalized between centrality. So the proteins that are on the very far right side are going to be the ones that interact the most. And the proteins that, if I sweep down from the top going down, this is the highest between centrality protein. This is like finding a needle in a haystack because that protein that we found was implicated in a breast cancer. And so we worked with physicians and medical researchers for trying to understand, are there proteins that are hidden up here with a high between centrality, but they don't interact that much, but they're very important to the networks that we have for cells to operate correctly. Now, we talked a little bit about streaming, and I'm very passionate about streaming. because this goes back to the question that was asked a little bit ago. Today, we have some fantastic supercomputers, high-performance computers. I have one picture here, and they're really, really great for taking a static data set, loading it in, and to be able to run analytics on it. This is the way that we've been doing graph data science for a long time. And I think of that as reporting the news. Something bad happens, you load in a data set, you analyze the data set, and then from that, you try to figure out, for instance, after my company is attacked with a cyber attack, I want to figure out how did they get in, what did they touch, what did they take, what did they damage, and something egregious has already happened, but I'm doing forensic analysis. And where I'd like to get to, and what I'm passionate about, is building systems to do what's on the right, the streaming analytics, which is going to be more predictive. I want to do predictive analytics, where I want to figure out something's about to happen and to protect before something egregious occurs. So this really requires new thinking about data structures. What does it mean to have streaming or dynamic graphs? And as I was saying before, you could have data coming at you from a fire hose where you have to make decisions in milliseconds, or you may have problems where you have a graph and every minute, hour, day, or week, you get a new batch update, and you want to take your existing graph and then see how does that new batch update impact your analytics on that graph. And often that graph is large, so you don't want to boil the ocean every time or recompute from scratch. You want to take the answers that you had before and see how this much smaller batch update then impacts the algorithms that you have. For instance, what communities exist in the graph? Are there more shortest paths between vertices like you didn't have before? Has something structural changed in the graph? Are there new communities in the graph? And you want to do that in time that's proportional to that update, rather than having to recompute maybe over trillions of vertices. I'd more like to save my partial results and compute over maybe my batch of 1,000 new edges or vertices. So that's the challenge. And we were, question. So I'll repeat the question, or yeah, you can say it into the microphone.
Yeah, so I was asking, what is a sparse problem and what is a dense problem?
Oh, great question. So I use sparse and dense over here. What that means is if I think about a graph, I have an adjacency list for each vertex. So I'm vertex 1, and I have friends, vertices 2, 3, 4, and what typically happens in a social network is that if you think about your adjacency matrix, we don't actually build this, but you think about your adjacency matrix as a matrix where each row is the adjacencies to a vertex, and for each column, when you are a friend with a person in that particular column, you just put the number 1. And what turns it out is that that's a sparse matrix because many of the entries are going to be zeros. Think about your favorite social network. You may have a couple hundred friends, but you certainly don't have 3 billion friends. And so if I build a big matrix of everyone who is friended with each other on Insta or Facebook or LinkedIn or any of your favorite networks, what you'll see is that it's a very, very sparse graph. That's what I mean by sparse. Dense, on the other hand, often are the types of problems that I see coming from computational science, where my matrices have values for almost every entry. And so these types of supercomputers that we see today work really, really, really well when you have dense problems like computational science, where my matrices are coming from computational fluid dynamics, or they're coming from other sorts of physics problems where I have values and floating point numbers in every entry. But when we're looking at these types of social network problems in graph data science, we're in a different regime. And what tends to happen is, rather than taking these dense rows from the matrix, being able to stream them through processors and run operations on them, what we tend to do is take all of those entries and we spread them across the supercomputer. And if you think about what an operation is, I'm at a vertex and I have another friend that I see because we're adjacent. So I go to my other vertex and they have a bunch of adjacent friends. And if I'm trying to figure out who are my friends of friends, what I basically start doing is walking around randomly through the memory system in that computer, rather than just streaming vectors through the processor. And so these graph problems tend to become very memory centric. I don't have a lot of locality because what I'm doing is latency to memory to figure out where to go next, where to go next, where to go next as I jump around a graph. And so machines that have caches and deep memory hierarchies, that actually gets in the way often because I don't have a lot of temporal locality or a lot of spatial locality. There's some, but there's not a lot. And so caches I'm bringing in a big cache line, but I just want a word out of it, and I'm not going to reuse it again as I'm walking through the graph. So hopefully that explains a little bit about dense versus sparse and why some of the existing machines and supercomputers are really challenged to do these types of graph analytics. Does that help?
So, better storage data structure for these graphs should help, right? Because
I can repeat the question. So that the question was a better data structure for these graphs should help.
yeah, because it seems like the operations themselves are not computationally intensive. It's mostly stalling on the memory itself, like randomly walking around the graph. So better storage structure for them, more compact, that can also be used by the caches and all, should help.
So yes, better data structures do in fact help. But if there's no locality, then the caches really don't help us that much. They can help some, but often they don't help much. And when I look at what tends to happen is that even though I have a good data structure, if it's a really large graph and it's spread over the memory of a large cluster or supercomputer, what tends to happen is I'm not operating in memory cycle time like nanoseconds that I would in a floating point computational fluid dynamics or scientific computing problem, but I'm working at network speeds now because what happens is even if it's a global shared memory system or a PGAS system or message passing, I'm now having to send messages around the machine, and that takes tens to hundreds, even thousands of cycles to go between the system. And so I'm often running at these memory and network speeds rather than just in my processor cycle. And I don't have a lot of work. When I get a vertex, what am I doing? Often I'm just looking at who their neighbors are. So I don't have a lot of floating point operations that can hide the latency for those memory transactions. Question?
So you mentioned that in case of streaming analytics, you want to preserve the pre-computed values and use them to reduce the amount of computation, right?
Yes.
But you also mentioned that you are memory bound.
Yes.
Doesn't it make more sense to decompute than to keep something in memory and fetch it back?
So great question, but I'll give you an example on this next slide and we'll come back to it. So this, well, sorry, I hid my next slide. So this isn't the one this is. This is the slide I expected. So in 2009, we were the very first group in the world to take all of the public tweets. And if you think about Twitter in 2009, nobody knew that you could become US president on Twitter and do other things. But in 2009, we decided to see, is there anything good about Twitter? We took all of those tweets and we streamed them into a very special purpose supercomputer. Now it's in museums, but it was called the Cray multi-threaded architecture that was purpose built for graphs. There are specialized machines that you could do for graphs like this machine. I love this machine so much. If you had any other work to do that wasn't a graph, poor performance, very, very poor. But if you had a graph, this was the ideal dream machine for you. There were no caches in the machine. All memory was decimated, both logically and physically, to ease memory bandwidth issues. So you're using all of bandwidth of the memory. And it basically was a latency tolerant machine. Absolutely fantastic. So we decided to do this big graph problem. And over September and October 2009, we loaded all of these tweets into the machine, and we constructed some graphs of followers and followees, what were key hashtags. And then we looked at breaking events, and we were trying to ask, could you identify during a breaking event which were the Twitter handles that you would want to tune into to have the most influential handles. So often, I mean, today we have more problems like understanding sources of misinformation. That would be very similar. So here we looked at two events, and I'll just use one of them, for example. The column on the left, H1N1, was an outbreak, another pandemic. Prior to COVID, it was an influenza virus, H1N1, that the Global World Health Committee thought would have double-digit mortality. Luckily, that didn't occur. But what we wanted to do was figure out where are people getting their information from. So we ran our parallelized between centrality algorithm that finds the most influential vertices in a graph. And we were able to run this in near real time. And what we did was we built the graph in the memory of the supercomputer, and we left it there. We could update that graph as we had new tweets that were coming in. We could keep updating, and at the same time putting out the updates of the between centrality score, so we'd see that ranking change. So there's no ground truth. This isn't proof that this works, but this is really an ad hoc demonstration that we could run such a system. And again, we were the very first group in the world to analyze all public tweets. And the answers that we got out were very interesting. So we saw some of the top ones, like number 1 is CDC flu. I know it's a little bit hard to see in the room. Number 12 is CDC emergency, 13 CDC eHealth, number 4 flu.gov. What these are all the United States Centers for Disease Control and Prevention, the CDC, that is one of the primary sources for understanding health in these matters, and it was their accounts that people were luckily listening to. We also saw commercial news being top-ranked information sources. For instance, number 5, New York Times, number 8, CNN, number 11, Time Magazine. That's what we'd expect. And then we got these surprises. So number 3, official PACs. I don't know if does anyone even know what official PACs is? Would you tune into them during a breaking event of a health crisis with a new virus that's propagating? Probably not. So any guesses what official PACs is? Never guess. So it turns out there was this gaming convention, Penny Arcade, and in fall of 2009, mostly adolescent males were getting together in Seattle in the United States because they all traveled in. They're really the first group in the US, ground zero for H1N1. They started tweeting with each other, hey, you know, I don't feel so good, my nose is running, I have a fever, you know, how are you? Same thing. Hey, did you go to the doctor? Yeah. So people were getting their information on the symptoms of H1N1, and also they started tweeting with each other, hey, are you dead yet? No, I'm not dead. Are you dead? No, I'm not dead. I mean, very fascinating tweets. But that was one of the best news sources to understand the disease itself, because it was a novel influenza virus that the world hadn't seen before. You never would have thought about tuning into them. But also, I'd like to use this example because I used this slide actually in India a number of years ago at a conference. I talked about this work. And one of the students in the audience must have been the #1 fan of a music group, the Backstreet Boys, number 9. Anyone hear of them? Boy band from the US. And that student wanted to know, why is the Backstreet Boys up there? And I thought, well, I don't know. You know, this is a great question. So we actually went back to the data and we did some analysis. And this was a great indication of when you often have to go back to ground truth, because there's a new album. Today, you probably don't know what albums are because you download everything or stream it. You used to have to go to the store and you'd buy a record that would be, you know, that you put on the phonograph, or then a CD that you would put into your CD player in your Walkman. Back in the day, the Backstreet Boys released an album and then people were tweeting, hey, I don't think I have H1N1, but I'm going to go to the store and buy the new Backstreet Boys album. And so the two pieces of information got crossed with each other. And so the Backstreet Boys had nothing to do with H1N1. So that hopefully answers why we keep the data in memory. So here we had, at the time, terabytes, which was a very large size, that we'd want to keep in the memory of the machine and then have analytics that could run on top of it continuously, rather than to spend time to recompute or to reform that graph. So let me move forward, and this is really the work that I wanted to talk about, but I'll speed it up a little bit. We are working on a National Science Foundation project right now called High Performance Algorithms for Interactive Data Science at Scale. And what we're trying to do is democratize supercomputing and data science to let anyone in the world who knows data science be able to work on massive data sets. And when I mean massive, it really is the case that our data sets are getting bigger and bigger and bigger. So you may have data sets that fit on your laptop, or maybe they're in the cloud, but at some point you may get data sets that are tens of terabytes or larger in size, where current technologies just don't scale. And your capability for solving these problems, today the average data scientist, they don't know C, C++, Java, Fortran. No, they know Python, right? Python is now top language for data science and programming. So we have to be able to let someone who just knows basic Python, for instance, using NumPy and Pandas for data science, to be able to run these new analytics on potentially tens of terabytes of data. So we're building a system to do that, and it's called Arcuda, and I'll tell you a little bit more about it. But I do now add this dedication to my very good friend and technical collaborator for decades, Mike Merrill, who passed away just last month, who was really the heart of this project. And so I want to just give him credit and recognize him, gone too early. But he was one of the founders of this project. And the idea is that we would marry productivity using Python with high performance computing using an open source compiler called Chapel that the Cray supercomputing company has been developing. Started about 20 years ago under a DARPA high productivity computing systems program. And a year or so ago, HPE acquired Cray. So this is now HPE's Chapel compiler. It's a project that they're supporting. And we want to use it to build this system that I picture over here. So I have a user who just knows basic Python, and they're in their Jupyter notebook writing their Python code. But at some point when the problem gets too large, they can use Arcuda, where they simply change out the NumPy and Pandas routines for some of our routines, very similar code. But what's happening on the back end, whether it's a laptop, a supercomputer, a cluster, a large shared memory machine, we can have massive data sets that are remote. And we have ZMQ, a zero message queue, that's going to pass messages back and forth. So the user has the illusion that they're just on their laptop in their Jupyter notebook. They ask a question, they get their answer out. They don't know anything about supercomputing. And what we're designing is primarily Chapel code. It's a variant of C, C++ that lets us productively work on very large problems. And there are a number of modules in Arcuda, and we're building out graph analytics. So that core graph analytics we call Arachne. Arcuda is a Greek word for bear. Arachne is a Greek word for spider. And so we have some algorithms that are available. And in fact, we have analysts today using our graph analytics. There's probably about 20 analysts who are running our code. It's in GitHub, so anyone can go and download it. I think the links are here, but if you search GitHub for Arcuda, you'll find it. And it's all open source. And I encourage you to give it a test drive, see what you can do with it. So our major contributions are building out large-scale graph analytics on top of Arcuda and extending it by having a new novel sparse graph data structure. So as was mentioned, data structures are important. we're a little bit limited by Arcuda in that everything's got to be a 1D array, but we built a sparse data structure. And then we're making it very easy for data scientists to use this and to build graphs that have billions or trillions of vertices and run interactively. You type in your query, you get your answer out, rather than having to wait hours or days to get a result. I don't have time to go through all the details, but we have a data structure that allows constant time queries of a vertex to an edge or an edge to a vertex. Question?
Microsoft has this product, Gremlin database, graph database, so how it differs from that? I mean, you write a query and you get answer for billions of nodes.
So great question. And there are some good graph databases out there. For instance, Neo4j, TigerGraph, and others. But they often don't scale to these sizes. What we really have is a number of queries. For instance, an analyst wants to run between centrality on a graph, or they want to find, for instance, find me a small connected component less than 50 vertices that has vertices of this type in it. So we have analysts who are asking questions rather than, if I take a step back, graph databases are good where you have perfect and complete information. So often you're looking at financial transactions where you don't want to miss anything and you want ACID compliance and so on. Where we're operating often is where we have very messy data coming from social networks, coming from network traffic, where it's fuzzy, there could be incorrect information. We don't need all of the engineering that goes into a graph database per se. So while there's a lot of similarities between what we're doing here and graph databases, I think those are often targeting two different types of use cases. Question?
What are the dataset sizes you are operating on this algorithm?
So the question is, what are the dataset sizes that we're operating on? For Arcuda, it's built to operate today. It's being used in some environments with data sets that are 20, 30 terabytes in size. It will work on your laptop with a data set of, a megabyte. And so it's really a scalable system that is able to really process any size data set to the limits of data that we have today.
And all these compute operations of a graph are being done on CPU or GPU?
Everything right now is CPU, so Chapel just targets CPUs. However, HPE is working on Chapel for GPU acceleration. And so that's actually coming, I believe. I don't speak for HPE, but I believe that's in the roadmap that it will be GPU accelerated.
And what kind of parallelizations are you looking on? Do you use a task for it?
Excellent question. And I love talking here because I love having questions and interaction. And this is absolutely fantastic. So Chapel has been built to give you different, I have some examples in the slides coming up that I may or may not get to, but it's very productive. So I can have, for instance, a bag of items that sits on Chapel, different types of distributed arrays. Chapel provides a lot of that for me. So the parallelization and the control of it, I leave to Chapel to do. And it's very easy then for my students to program it. And normally it takes one of my students about a month or so to become a Chapel expert for developing in Chapel. But once they do that, they find that there's many different ways to do it in Chapel. It provides a lot of constructs at a very high level to be able to do these types of manipulations for the graph algorithms. You're welcome. So I'll move forward in a few slides, but basically we have ways to read in inputs on the upper left. We have sort of a query engine, then we have a bunch of algorithms, and we can also run a number of benchmarks. So the algorithms that we have papers about all of these, and this is a lot of development in the last year. I have very, very good graduate students and undergraduates working with me as well. I even have some high school, pre-college students who have been contributing. So it's just been fantastic. But we've implemented breadth first search, connected components, new algorithms like trust analytics that I spoke about this week in Bangalore at the High Performance Computing IISc conference, Jaccard coefficients, triangle counting, triangle centrality. So each one of these are, in fact, triangle centrality is a new type of centrality that was invented by a colleague of mine, Paul Burkhardt, last year. And so we're able to implement a lot of graph algorithms very quickly in the system and let our analysts use them. Some of these are surrogates for community detection, like trust analytics is based on finding triangles in a graph. So in a graph, if I see a triangle, that means 3 vertices are connected. And if there's a subgraph where I have more triangles in that subgraph than I do elsewhere in the graph, that's sort of a denser component and kind of a surrogate for finding a community. And a lot of analysts like to be able to say, you know, given this trillion vertex graph, find me places where I can find a very high triangle supported subgraph. And that's essentially what trust analysis is. And there's a lot of contributions that we've had in designing these algorithms, new ways to parallelize them, new algorithms, better performance, new optimizations. So any one of these could be a talk to itself. Let me just focus on one or two, like triangle counting. Here you see 9 vertices, and hopefully, how many triangles are here? It's not a trick. I think 5. 1, 2, 3, 4, 5. Okay, it's not one of those tricks like how many triangles do you see here? Pretty straightforward. So there's 5 of them. That would be the answer. And so the code that we have this is pseudocode from Chapel, but it's really this easy where we're going to iterate. We have things called locales. That's what's running together on each node. We're getting the adjacency lists. We're trying to find wedges, and then closing a wedge gives us a triangle. So we find 2 paths and then a closing edge that would make that 2 path into a triangle. So it's a very simple search that we have. We're using a number of Chapel constructs to do that. But we also have optimized it into something that we call minimum search triangle counting. And I don't have time to try to articulate all of the details of this, but maybe we're at U and V, and we're going to examine vertex U to see any triangles that have U and V. We'll launch a few threads, W1, W2, W3. They're all searching for adjacencies, but we're going to do this in such a way, I won't go through all the math, but we're doing it in such a way to minimize the number of checks, list intersections that we need to make. So if we do this in the right way, and we have big adjacencies and small adjacencies, we want to use the smaller ones to reduce the search size. And I have a couple of examples here, but needless to say, we have an algorithm now that is novel. It does less comparisons to do that triangle counting. We also do connected components, and connected components is just, most of you are probably familiar, set of vertices in the graph, the maximal subgraph that is disconnected from the rest of the graph. So often we're trying to find connected components. We have an optimization as well for doing connected components. And then I won't go through this in detail, but this is just my Jupyter notebook of a demonstration of using our Arcuda, where we connect to a server that is holding the graph. And then we can run our analytics. Here we're doing, I guess you can't see it, so I can tell you it's doing anything. But we can tie into other packages like NetworkX to visualize small parts of the graph. But here we're basically doing some basic graph algorithms. In here we're trying to find the vertex of maximum degree. Then maybe we use that vertex. We lost synchronization again. So I'll talk through it as I think I probably have to reconnect to Teams. Arcuda and Arachne graph algorithms. We took that vertex with max degree. We ran a breadth first search from it. We get answers. We display it over here. It's all good. We tested this on a variety of inputs and both real world examples and some synthetic graphs. And the performance was great. So we're able to scale to very large graphs. And again, I won't go through all the details. Some algorithms run faster, some don't. But in most cases, we do quite well. One of the most expensive parts is actually constructing the graph for the first time. So in practice for real world graph problems, often you construct the graph and then you have multiple analytics that you run on it. So it is a heavy hit to create the graph. But once you have it, you can run your analytics much faster, synthetic graphs. So again, we have a lot of publications in this area. These are just the papers about Arachne and Arcuda that we've written in the last year. So it's a very productive group that we have. And the paper that we did this fall for IEEE HPEC is the paper that describes the Arachne system, kind of the overview paper. So just to conclude, we've been able to use Arcuda and Chapel to do really high performance, scalable graph data science. And there's still a lot of work to be done. It's all open source, and we encourage others to try to pick it up, kick the tires, and see what you can do with it as well. It'll run on your laptop, or if you have a supercomputer, anyone in the world now could use a supercomputer to analyze the large data sets. And we also want to implement some new algorithms. We're looking at stringology, so string algorithms. We're also looking at trying to do property graphs, machine learning, a bunch of other things. And now a plug for this great book that just came out this summer that I had the pleasure of editing, Massive Graph Analytics. This is the book if you're interested in this field to pick it up. I get no royalties, so I make no money. It's all going to charity. I had to figure out a way for students to benefit from this. So again, I'm making this plug because it's a good book. And again, it benefits students. There's about 600 pages of goodness in there. Like this was one of my pandemic activities, was to work with about 85 contributors across 21 chapters, both from industry and academia, as well as labs around the world to write chapters on massive graph analytics. So it's got some of everything in there, from algorithms to applications, models, frameworks, and software, with a lot of contributors, sort of a who's who in the space. I was able to twist people's arm and get some great chapters in there. So I just really love that work that we put together. And on my final slide, I just want to acknowledge my current research group who contributed to this work. Dr. Du is a principal research scientist who's with me. Two of my 4 PhD students, Alvarado Rodriguez and Puhan Lee, did a lot of the work that's here. Oded Green, who was a PhD student of mine years ago that I collaborated with, he's now at NVIDIA. And then some of my recent alumni, including Joe Patchett, who just completed his master's degree doing the triangle counting and trust work. And then some of my former PhD students who are at academic positions, national laboratories, Google, NVIDIA, and other IBM and other places. So very diverse group of students that I've had. So again, thank you for making this very interactive. I appreciate you coming out and listening, and would be glad to take any other questions. Thank you.
Let us thank David for an excellent talk. Before I go to the people who are in this room, quite a few of them are online. If they want to ask any questions, maybe they can just unmute themselves and ask the question to David. Wait for a few minutes for them to ask questions, because we were 10 of them online. Sorry, so maybe you can ask the question. Yeah.
So Chapel is the compiler that is running on top of the Cray architecture. It's target specific to the Cray architecture, right?
No, so Chapel is the open source compiler. Yeah. You can go download it from HPE, but it works on Cray, now HPE Cray architectures, but it also works on, a Linux cluster with Ethernet or InfiniBand, works on a laptop. It works on any place where you have traditional nodes.
I see. So this Arcuda that you've built, so these are built providing on the abstractions that Chapel provides. You build this graph algorithms, is it?
Correct. So most of Arcuda is, there's components. There's the front end stubbed out Python routines for the user. There's the ZMQ, which passes messages from what you type in your Jupyter notebook across to what needs to be done on the large scale Chapel platform. Then there's what we spend most of our time on is developing the Chapel routines. And that Chapel, it could have been another framework that we use. We just chose Chapel because my colleague Mike, who recently passed away, really liked Chapel and wanted to, after so much was invested, 20 years of development from some amazing compilers folks, we decided that Chapel was the right tool for this. And so we built it in Chapel.
I see. I think one of my friends asked a question like, is this implementable on the GPU? So is Chapel does it support GPU as a target, or how much engineering effort would it take to design it?
So that's a great question, and actually HPE Cray, if you're very interested, it's open source. You can work with them to create a GPU target. I don't speak for them, but I do know that they're interested with finite resources of their team. It's a very good team that's been together quite a while. One of my colleagues, Michelle Stout, moved from academia last year to be a product manager for Chapel at HPE. I do know that on the roadmap they have targeting GPU acceleration, but I don't personally know where they are in releasing that. But it's a huge interest. And again, it's all open source. So everything with Chapel you can download and contribute to. I think I had a slide with a GitHub where we can get Chapel as well.
Thank you so much.
You're welcome.
So it felt like these algorithms are currently for static graphs, the Arcuda algorithms. Is that correct, or are they implementable on dynamically changing streamlined graphs as well?
Oh, you got me. So part of this talk, what we've been doing in Arcuda, the genesis of Arcuda was really 2019. And I didn't show you all of the work that we did with Stinger on streaming graphs, where we support streaming graphs. For Arcuda, we kind of had a walk before we can run. So we first are implementing on static graphs. And unfortunately, right now, we're limited to one-dimensional arrays. And it's very, very hard to update those arrays once we create the graph. However, I have colleagues, for instance, Rich Budak at Georgia Tech, Vivek Sarkar, and others that are working on multi-dimensional arrays and also new data structures and methods so that we'll be able to do more of our dynamic graphs or have graphs that change over time. So as future work, we're getting there. We first built a lot of static routines, as you saw, and you saw most of this work happened in the last 12 months. So we're there, we're working on property graphs right now, and then we're going to work as there are more data structures implemented in Arcuda, then we're going to get to streaming graphs. Great question. So again, how many times do you see a framework at the largest scale beyond what industry can do, beyond enterprise packages, being able to process terabytes and do it with just a handful of enthusiasts? So it's an open GitHub source code, MIT license, and we encourage others to contribute. But right now we're just doing it as fast as we can because we're so excited by it. But it's going to take a couple of years. And there are companies that have approached us about using Arcuda in products. So companies that you would have heard of in the systems area are now all looking at Arcuda. Now that we've built it out in the last 2 years or so to where it is, they're very interested in productizing it within other frameworks. Question?
So I'm assuming that the algorithms for static graphs are simpler to write compared to, say, dynamic graphs.
Yes.
If that's the case, then are there any automatic transformation techniques that, given an algorithm for a static graph, can automatically generate the algorithm for a dynamic graph? Are there fixed set of strategies to convert such static graph algorithms to dynamic?
So for the last, I don't have it in this talk, but for maybe, I don't know, at least 15 years, probably longer, maybe 20 years, I've been working on streaming and dynamic graphs, some of the earliest work in that space. And there's two modes of operation, primarily two. One is where you have your graph, you have data coming in, you update the graph, and then you run your analytic. Then you go back, you add more data to the graph, you run your analytic. The other form that we worked on is where you hold the graph in memory, the graph is changing, and concurrently there are analytics running on top of that graph. So we first developed in that environment, and that is very, very difficult. For instance, imagine you're running breadth first search, and you put a vertex in your queue, and then the next time you go to pop it out of the queue to explore it, it's deleted. You know, what happens? So we had to write algorithms that understood that the graph may change anytime underneath them. Edges could be added or deleted. Vertices could be added or deleted as you ran. So what did it mean to be correct? What did it mean to have the right output? And we had a lot of theory and implementations that tried to operate. And again, to an academic, there may be the perfect way of doing it, but we were working in places where it didn't matter. You needed an answer. We were working with customers that needed an answer. And you know, the best answer that you could provide, the fastest, is what they wanted. Tell me if there's an insider threat. Tell me the best threats that I need to explore today, and be able to do it. I kind of drifted away or forget the
Yeah, so my question was that, is there any work where...
Oh, yes. So for automatic translations, what we found was that most of the time these increments really aren't derivable from the static algorithm. So often you write the static algorithm as your starting point, but then for an update, for instance, I've connected components, you have a new edge added. Well, that new edge, when you think about it, the logic you have to come up with, the edge can go between two different components, which it joins them, or the edge can be within a single component, which it doesn't change the connected components. And so you have to come up with this logic, or you go to delete an edge. Most edge deletes are safe because they're coming out of a component and not splitting the component into two more pieces. But every once in a while, rarely, an edge will now cleave a component apart. You have to detect that delete. Now you have to run connected components on each part to see who went here and who went there. So it's sort of a different logic. And there may be some cases, but I think in many cases, it's really hard to derive what that transformation should be.
I probably have one last question. I just wanted to understand both Arcuda and Arcane, are they more like a library-based approach, or do you do something more than that? Meaning, like, are there opportunities for you where multiple calls could be composed together and more optimizations?
So, I mean, right now it's really a framework like a library, and it operates very much so. We have our Arcuda, and Arachne is really a logical circle around the work that we're doing with NGIT, building graphs on top of Arcuda. So we contribute to Arcuda, but it's really, you know, a logical subgroup is the graph modules. But what it is just library calls. So we have to write the Python library call, we have to write the message queue calls for the message library, and then we have to write the Chapel backend Arcuda calls. And so they all have to be coordinated together, but it's really just, at the end of the day, library calls for all of them. And the user is just making library calls to the Arcuda package.
Okay. Do you see that there are opportunities for you going down the road that you could be doing certain optimization or composition of these things?
Yeah. So in fact, one of the areas we have table joints, and optimizing the order of the table joints would be a huge, that's open work that we haven't explored yet, but we are signed up to try to figure out other optimizations. So I think there are a lot of optimizations. As I mentioned, the idea for Arcuda came about in 2019, right before the pandemic, and then the pandemic occurred, and we could all work from home on it in our spare time at home. And then we're coming back into the office. But we started with nothing, and we've been building it up, trying to figure out now how do we go from 3 developers to 25 developers, and have people contribute, how to refactor the code in a right way. And so I think it's right now a really good opportunity to come, and there's a lot of optimizations that could occur. And you have to build it to understand what you did wrong and rebuild it. So we've been through a couple phases like that. But I think it's fairly stable right now as a base platform. And as I mentioned, we have dozens of analysts that are using it. In fact, we upload code from our side to GitHub. There are customers who pull it down from GitHub and are using it in critical mission capabilities, and it's working for them.
Great, thank you. Okay, if there are no further questions, are there any questions online? Okay, if there are no further questions, let's once again thank David for an excellent talk.
Thank you.
On behalf of the department, I would like to send some small memento to you.
Thank you very much. Thank you.